Now let's get back to physics that we are discussing. The next thing I want to discuss is explicit representations of spin operators. Okay. So far we have looked at angular momentum algebra in an abstract way, right? So, but we want to look at these operators explicitly and also look at what the state vectors look like explicitly. So here we are going to address the question for spin. For the eigenfunctions of the orbital angular momentum, we shall look at it later when we are discussing the hydrogen atom. Okay, so let us recall, suppose that we have a particle with spin s and z component of spin given by m. So what does this mean? That s squared acting on sm is what?
S times the eigenvector.
Someone wants to correct Nahi? What is the eigenvalue of this thing? You're supposed to look it up by yourself.
Will it be s bracket x plus 1 or something like that?
Yes. Why doubt? Did you not work this out? I told you.
No, I was supposed to, but I forgot.
Yeah. Can you just have a moment? Process here, no? Process here. Yeah. Yeah, you're supposed to work this out. Okay, good. And then there is S plus acting on S comma M, and that is going to give me square root of S minus M times S plus M plus 1 times S. Ekhane ki bothabo? What would be the M? What would be the value here?
M plus 1.
Excellent. And then S minus S comma M, and here you have S minus M plus 1, S plus M, and here you get S and M minus 1, right? So these are the stuff that we will use. So if I choose the value of the spin to be S, what will be the dimension of the matrices? Another way of saying it is, what would be the number of eigenvectors of the Sz operator? The dimension of your Hilbert space.
I'm not sure, actually.
Okay, anyone else wants to try? Remember the ladder?
Maximal of value that M can take, and from that twice S plus 1 should be, I think,
Yeah.
the dimension.
It should be twice S plus 1 is the dimension. Okay? So if I take S to be half, then the dimension is what? 2, right?
Mm-hmm.
So let's look at this case explicitly. So our basis will consist of a state where S is half, M is half. And then if I apply the lowering operator, I will get S is half, M is minus half, right? But if I apply the lowering operator once again, I will get 0. So if I apply lowering operator on this thing, I get 0. If I get the raising operator on this thing, I get 0. So these are the only two basis vectors. So because the value of S is fixed, we can forget this for the time being and introduce a notation that is convenient. So it's a notation. Call this plus and call this minus, okay? So this means that if I take SZ and apply it on plus, I get half plus. And if I take SZ and apply it on minus, I get minus of half, right? Now what we can, so this is just this equation. Now we can also write down what these equations will look like. So if I apply S minus to plus, I will get S minus will give me S minus M plus 1. S is half minus is half plus 1. Then S plus M, which is half plus half. And economic level, I'll get minus. So this is going to give me just, what is it going to give me? This plus this is going to be 1. So I'll get
1 will be the answer. Yeah,
this thing, right? So now if I apply S minus to this thing, I will get 0. And you can explicitly verify that. Similarly, if I take S plus and apply it to minus, then I will get plus. And if I apply plus again to this, I will get 0. So now let's work out what SZ is. So SZ or S3, as I've been calling it until now, can be thought about as, so I can insert the identity here and another identity here, right? I'm just using the fact that the identity operator is the sum of the basis vectors, where I goes from minus to plus. So this means that I can write this as a matrix element where S3ij is the matrix element, and the row, the column and the, here there's an I will multiply j and they'll give me a delta function. So one of those, oh yeah, sorry. This is so I misspoke. So here, what is S3 of ij? This is defined to be I S3j. Okay, this is what we call the matrix element. So if I choose my basis, this is what so let's work this out. S3ij is going to be plus S3 plus, so this is going to be the row, plus S3 minus, so this is column, minus S3 plus minus S3 minus, okay? Are you following what I'm doing?
Yes, sir.
Yeah, I'm looking at this particular operator in a particular basis. So now, we know what this is. This is just half. This is also, we know, it's this S3 acting on this thing will give me minus half minus. But the minus state and the plus state are orthogonal, right? So this is going to be 0. Similarly, this is going to be 0. So what I'll have is that half on this corner and minus half on this corner. Okay. So we can write this as the S3 matrix as half times the sigma 3 matrix, where sigma is the Pauli matrix. Okay. So you're following what I'm doing, right?
This is pretty amazing.
Yeah, I know. So S minus, this is the power of mathematics. S minus ij is going to be plus S minus plus, again, this is the row and this is the column, plus S minus minus. Now S minus plus minus S minus minus. Okay. Now you know that S minus acting on minus is going to give you 0. Now S minus acting on plus is going to give you minus. So this is going to be minus, but this is orthogonal to this thing. So this is going to be 0. S minus acting on this will give you 0. So S minus acting on this thing will give you minus, and this thing will give you 1. So you get 0, 0, minus 1, 0. As advertised, this is not a Hermitian matrix. Now, similarly, you can work out what S plus is. So S plus is just going to be 0, 1, 0, 0. And we can just take this thing, take its Hermitian conjugate, and that is going to give me S plus. And then I can work out what S1 and S2 are. From the definition of S plus and S minus, remember, S plus minus was S1 plus minus I of S2. If I invert these relationship, I get S1 is half of S plus S minus, and S2 is going to be 1 over 2I S minus minus S minus. So now if I plug in the value of S plus and S minus, I just get half of 0, 1, 1, 0, which is half sigma 1, the first Pauli matrix. Similarly, S2ij is going to give me half 0 minus I 0, which is half times sigma 2. So we have figured out the spin half representation of the angular momentum algebra. And of course, obvious in this is, in this representation, this is going to be plus 0. And in this representation, this is going to be 0, 1. Okay. Now, what will be this thing? Can anyone guess? Okay, what is the eigenvalue of the S squared operator for spin half?
Spin half. It's half and half. Wait, no.
Half times half plus 1.
Yeah. So
What is half times 1?
it's just half. So it
No,
becomes
half
1.
times half plus 1 is not
Oh
1.
yeah,
It's 3 halves, right?
yeah.
So 3 half times half কত হয়?
It's 3/4.
3/4. Okay. So 3/4 আমি কোথায়, where should I put the 3/4?
Diagonal.
Okay.
I
And
see.
if I were to reinstate the value of h, this would be h squared. Here there would be h, 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 h. Okay. All right. All right, good. Any questions?
No, sir.
Okay. So it might seem all of this is a little boring, but I'm telling you, this is actually worth doing. Because you know, it brings the algebra down to earth. You know, matrices, and you know, like how people think that, oh, all these abstract stuff in quantum mechanics, you know, all these algebras, blah blah, you know, I don't understand the physics, it's very abstract. But you see, it's not very abstract. It is one step away from, you know, actual matrices you can work with.